Okay, example 4. So this is exactly the same truss that we had before, except this time it's been rearranged in terms of its orientation. Let's start with E and A. So it says GPA. 1 GPA is equal to 1 times 10 to the 6 kilonewtons per meter squared. And incidentally, it's also equal to 1 times 10 to the 9 newtons per meter squared. So obviously the difference between 1 times 10 to the 6 and 1 times 10 to the 9 is due to this kilonewtons. So 1 GPA is 1 times 10 to the 6 kilonewtons per meter squared. A in this case here, so we therefore have E, and that's going to be equal to 200 GPA is equal to 200 times 10 to the 6 kilonewtons per meter squared. And then we have A, which is equal to 0.1238 meters squared. And then from these two, the product of EA is going to be equal to 1.6 times 10 to the 5 kilonewtons. So obviously you can see the meter squared and the meter squared cancel each other out. So we get an answer in kilonewtons, which is what we want. But of course you can use any units that you actually want. Now we start off with the equation as before. WV external virtual work is equal to WV the internal virtual work. And then that one comes from equation 18 in the course notes. So this one is equal to the integral of nx n bar x, where that is the virtual that's the virtual force, divided by EA, which can be a function of x, dx. Now for a truss system, so these aren't beams, they're trusses where the axial force is constant and EA is also constant, so we're just getting to the sum of all of the forces in each of the members of the truss. So for the case of a truss, that can be expressed as n bar L over EA. So there's nothing new about that. We're just saying that's how we get from equation 18, which to the case of a truss, where it can be expressed as the sum of all the axial forces multiplied together by the axial forces by the unit load. So by the unit load, which is 1 kilonewton, multiplied by the length of the members and divided by EA. And in terms of the other side of the equation, it's going to be delta, which is going to be the deflection that we're after, times this 1 bar, which is the unit load in terms of kilonewtons. Let's just do a non-dimensional analysis since we're here. That's kilonewtons squared times length, force times length. So so not length, meters. EA, as we've seen before, has units of kilonewtons. That has the units of kilonewtons. So when we express our delta, we'll be doing delta equals 1 over 1 kilonewton multiplied by something with the units of kilonewton squared times by the length divided by something also with the kilonewton. So we can see all of that cancels out. So we would expect our answer to be in terms of meters. Now let's have a look at the truss member. So let's have a look at the truss down here, and then that goes up there. That goes probably down here, and then that goes down there, and then that would go up there, and then that would come down. So that's exactly the same truss as before. Now on the other side, there is also another truss which is also identical. So let's just draw that one out as well. So it's actually symmetrical, which is which is handy. Now, we've got this 100 kilonewton jacking force, so we've got the jack there, and that's going to be like 100 kilonewtons, and the jack's going to be pushing on both sides, so it's going to be 100 kilonewtons per actual truss. So the load path, you could expect the load path of that to be going, certainly you would expect the load path to be pushing that member and also that member. So we've drawn them consistent with tension equals positive. But we would expect the axial force in that member to be negative, and we would expect the axial force in that member to be positive. So we would expect the axial force in that member to be negative because it's pretty obvious that that member's in compression. Now, under this system of loading, what we could do is let's just take the 100 kilonewtons, which we've got acting there, and then let's say that member is number 3, so it might be handy to label the members now. 1, 2, third member, fourth member, fifth member, sixth member, and on the other side we might just like to continue. Let's call it the 7th member, 8th member, 9th member, 10th member, 11th member, and 12th member. So we've got this 100 kilonewton force, and we've got this member here, which we're going to call F3, which we've drawn in the consistent direction of tension equals positive, but we would expect that to come up with a negative answer for F3. And then right here we might say F3 sine alpha. So we've got this angle alpha there, which is also the same as alpha there, and using the identities that we had worked out before, we should have had sine alpha is equal to 3 over 5, because that distance there is 3 meters and that distance there is 5 meters. So sine alpha is 3 over 5. Cosine alpha is equal to 4 over 5. So 4 over 5, because we know that from there down to there is 8 meters, and therefore we know that that distance there is 4 meters. So the cosine of that alpha is going to be 4 over 5, and then it follows that the tangent of alpha is going to be equal to 3 over 4. So that's what we did before, so no need to work out the angles. F3 sine alpha plus 100 by equilibrium of the joint is going to be equal to 0. Therefore we get F3 times 3 over 5 is equal to the negative 100 kilonewtons, which is what we would expect, and therefore we will get F3 is equal to negative of 500 kilonewtons divided by 3, and that's going to be equal to the negative of 166.7. So let's just write that force there as negative, obeying the sign convention of tension is positive, but you can have any sign convention you want, negative 166.7 kilonewtons. And of course that member, being symmetrical, is going to be the same, negative 166.7 kilonewtons. So let's do equilibrium of the joint again, but instead of looking at the horizontal direction, let's look at the vertical direction. So before this F5 didn't come into it, let's now talk about let's now talk about vertical equilibrium. So F3 cosine alpha, remember that angle is alpha, plus F5 is going to be equal to 0, therefore F5 is equal to the negative of F3 cosine alpha, which is equal to 166.7 kilonewtons multiplied by 4 over 5, since 4 over 5 is what's in the cosine alpha, and that's equal to the positive 133.33. So that tells us that that member there is in tension, because we got the positive sign, and it's in tension by 133.33, and that member 5 is also, it's identical to member 11, so it's got the same it's clearly got the same value for its for the loads being carried by the members. And of course, noticing the system, members 1, 4, 6 and 2, they all carry no load, because the load from the 100 is all going down through members 3 and 5, and similarly members 8, 12, 10 and 7 also have no load, i.e. so the load in all of these members is 0 kilonewtons. Okay, and the same applies on the other side to 2, 6, 4 and 1. So we've already solved the real system. So what we've done there is for the real system, and the real system would obviously have a real load, and the real system would obviously deflect. Now, where's the biggest deflection of the real system? The biggest deflection is going to be at those 2 points that we've just circled up there. So if and the question asks, what is the resulting change in separation between the tips of the trusses? So those tips are where we've just circled. So clearly, in order to proceed with the question, we need to apply our unit force of 1 kilonewton meter to work out the n bars due to the virtual force, which occurs without any virtual displacements, but we can just work out the virtual forces in each of the members, and then we sum all of that and work out finally work out what the deflection of the beam is going to be. Sorry, the deflection of the truss is going to be.